this second session, I want to talk about impedance transformation, and then I want to talk about standing wave ratio and also the maximal signal locations and also minimal signal locations. So let's first think about that we want to read the input impedance at some location on a transmission line. And in the last session, we determined the reflection coefficient right at this point. But now, if we want to know the characteristics of the line at this location, we need to find out the input impedance at z equal to minus L. And if you review a little bit, in lecture 3.2, we derived the input impedance to be like this. And so you can organize the formula into this form and then define the reflection coefficient at L equal to this value. Basically, it's the gamma multiplied with exponential minus j to beta L. Or you can take the magnitude of it and then multiply with this term. And when you write down this expression, you immediately understand that the gamma L at this location is equal to also the magnitude of the gamma you look into this location. So if you don't consider the phase, the magnitude of gamma is always the same on a transmission line. That's why that we draw a circle on the Smith chart for a given transmission line. And so the input impedance at this location now can be organized into this form derived from this expression. And again, there's a real part and imaginary part associated with it. And you can see that this form is the same as this form, except that this Zi is the input impedance at this location, and ZL is the low impedance at z equal to 0, and gamma L here has an additional phase, which is exponential minus j2 beta L. So with the same form with a phase difference between this gamma L and gamma, then we can try to derive this gamma L subject to a known gamma at the low. So let's do this impedance transformation. So the difference between gamma L and gamma differ by this the phase term. So if you know this the gamma value on this the Smith chart, for example, at this location, then the additional phase term just means that you want to rotate this gamma along this circle for some angle. And because this 2 beta L has a minus sign here, so this means that if you want to convert this gamma into gamma L, you need to add additional negative phase angle to it. So for a negative phase angle, you want to rotate downward direction or along the clockwise direction. So if you rotate the point of gamma in the clockwise direction by an angle equal to minus 2 beta L on the SWR circle, then you'll be seeing the value for gamma L. So this is how you derive gamma L at this location with respect to the gamma at this point. And because we try to use the gamma value to find the gamma L value here, and so we're moving toward the generator. And moving toward the generator is along the clockwise direction. So if you look into the Smith chart, quite often you can see a label WTG. It means that the wavelength toward generator, that is the direction corresponding to clockwise direction. So if you move in the clockwise direction, then you'll be walking down the transmission line toward the generator. And for a full revolution of this motion, it's going to correspond to 2 pi phase for this 2 beta L. So a full circle of the motion will give a phase change of 2 pi. And if you put beta to be equal to 2 pi over lambda, then this means that a full circle also corresponds to half wavelength. So if you start from this point called 0, then at this point it's going to be a quarter wavelength. And if you continue to move down and back to the original location, then you will be moving half wavelength all the way from this point and then back to this point. And that's why that this W is labeled as wavelength, because a full revolution of the circle gives you a half wavelength. Now let's look into one example. For example, still we use the last example with the low impedance right here, equal to 2 minus GA. And then we want to know the input impedance at this point. And this location is the 0.1 wavelength from the end of the transmission line. So initially we want to identify the gamma value at this location. And we just found it in the last session, which is the point A right here. And this point A corresponds to a length 0.287 wavelengths on this chart. And although this A is right at z equal to 0, but if you take this point to be 0.25 wavelengths and take this point to be the 0 wavelengths, then this point is 0.287 wavelengths. And this is just a reference number. That does not mean that this point is anything to do with the length on the transmission line, because this point is located at the end of the transmission line. But you know that if you take this as a 0 point as a reference, then on the Smith chart, it's going to tell you that this A corresponds to a value of the wavelength equal to 0.287. Now, you want to move the 0.1 wavelength from this z equal to 0 point to this location. And you want to move it toward the generator, because your generator is somewhere here. So you want to do the clockwise rotation and just move 0.1 wavelengths to the 0.387 wavelengths. Then you will be intercepting this line with your SWR circle at B. And I want to emphasize again that for a given transmission line, your SWR circle is already fixed. So when you move on this line, it corresponds to you moving on this SWR circle from A to B. And so once you have this point B, you can start to read the input impedance at this location. So this B intercept with the RL equal to 0.6 circle. So this red circle is the gamma values subject to RL equal to 0.6. And this branch of the circles correspond to XL equal to minus 0.66. That is your normalized reactance at this B location. So once you have the RL and also XL, then you know the normalized impedance to be equal to 0.6 minus 0.66 GA. This means that the normalized impedance at this L equal to 0.1 wavelengths is equal to this value. In reality, you still have to convert this value back to the unnormalized input impedance. If you know the characteristic impedance of your transmission line, then you simply multiply this value with the characteristic impedance of your line, then you will have your input impedance at this location. So this is the example for you to find out the input impedance somewhere on the line subject to a known low impedance at the end of the transmission line. Now, sometimes we want to know where you can find the maximum voltage and where you can find the minimum voltage. Or you could also be interested in knowing the maximum current and minimum current locations on this line. So basically you search on this line and try to find out the maxima and minima values. So we come back to these two expressions describing the amplitude of the voltage and current. And previously we know that for the maximum value of voltage and minimum value of voltage, the phase is going to be equal to minus 2n pi. And on this plot, the 0 point is here, and as I just said, the quarter wavelength point is here. And but in the polar coordinate system, the angle starting from this point, and so the angle, the 0 angle is here, and 2 pi angle is also here. And when you move along this direction, this is the minus pi angle, and then if you go a whole circle, then you have minus 2 pi angle. So don't be confused that the blue labels the length of the transmission line in unit of the wavelength, but the red label tells you the angle on this Smith chart. So now we're looking into the angle right here. So this means that in the last example with ZL equal to 2 minus 1J, the low point is here. So now you want to move on this transmission line toward the generator. Then you move along the SWR circle. And then try to find out where the phase is equal to minus 2n pi. And apparently, the minus 2n pi phase is on this axis, on the positive plot of the real axis. So you need to go all the way to this point and continue to move to this point to find the location of the maximum voltage or the minimum current location. So if you go from A all the way to this point, then you have to calculate the length of the line. For example, if you move from this point to this point, previously you know that this point A corresponds to a reference length equal to 0.287 wavelength. And at this location, the reference length is 0.5 wavelengths. So the length of the transmission line from A to this location is equal to 0.5 minus 0.287 wavelengths. But if you want to find the maximum voltage point or minimum current point, you have to continue to move on this SWR circle to this point, because this point corresponds to this phase angle. So you have to add another quarter wavelength to your solution. Okay, so finally you have 0.5 minus 0.285 plus a quarter wavelength length if you move from this low impedance toward the generator to find the maximum voltage value. So think about that you want to move on this line, and the total length you have to move is this much. And then at this location, you'll be measuring a maximum voltage or a minimum current. And if you are interested in knowing the maximum current location and minimum voltage location, then the requirement on this phase angle is changed to minus 2n plus 1 pi, which is the R multiple of pi. So for the phase angle correspond to R multiple of pi, is this line here. This is a negative portion of the real axis. So, for example, if you want to find the location of the maximum current or the location of the minimum voltage from this low impedance point, you start to move on this line, and when you start to move on this line, it means that you'll be moving on this circle toward the generator, and then so you move to this point, which satisfies this phase angle, and then the length from A to this point will give you the length where you can find the maximum current and minimum voltage. And from this point all the way to this point, the length of the transmission line is 0.5 wavelengths minus 0.287 wavelengths. Of course, you could be interested in locating more locations for the maximum or minimum signals. And previously, I told you that for transmission line, the period is half wavelengths. So this means that if you add this expression or this expression with integer multiple of half wavelengths, then you will measure the same signal. So the this expression tells you that you can repetitively locate the location of your maximum voltage and minimum current. And this again tells you that if you just repeating this motion on this circle, then you can continue to find the locations of the additional voltage minima and also current maxima. So the a short summary is that for the SWR circle intercepting the positive part of the real axis, you will find the voltage maxima or the current minima. And for the SWR circle intercepting the negative portion of the real axis, you will find the voltage minima and current maxima. So that is how you find the locations of the extremal signals on this transmission line. Now, we could be also interested in knowing the standing wave ratio from this Smith chart. So let's try to understand this. Well, previously we have the definition of the reflection coefficient like this. And on the real axis, the reactive part is going to be equal to 0. So your reflection coefficient will have a real value. And with this real value, then the corresponding RL value will decide this gamma R. And so this is on the real axis, the value of gamma is decided by the resistive part of the low impedance. And previously, we also have this expression for the standing wave ratio. And this is equal to 1 plus gamma, the absolute value of gamma, divided by 1 minus the absolute value of gamma. And you can reorganize this into this. Assume that you only look into the real part of the gamma, because on the real axis, when XL equal to 0, you only have real part of gamma. So that's pay our attention to the real axis only. And turn out that when you work out this gamma as a function of the standing wave ratio, you found that this is similar to this one. In fact, they have the same form, except that in this expression, you replace this RL with this S. So this means that on the real axis, if you can read RL from the standing wave circle, standing wave ratio circle, then you can determine this the S value, because the formula are the same, except that the S is replaced by RL. So previously we have such a SWR circle on the Smith chart. And then, for example, we have a low impedance right here. And then we go to this location. This is the point where you intercept the SWR circle on the real axis. And then just read the RL value. Then you will have the S value, which is the standing wave ratio of this transmission line. For this particular case, we can read RL equal to 2.6 at this point. And so we can claim that the standing wave ratio of this transmission line is equal to 2.6. And this is because of the same form for this expression and this expression on the real axis of the gamma chart or Smith chart. Now I want to summarize a little bit for this session 4.2, and the theme of this session is about impedance transformation, because quite often we want to decide the input impedance at a particular location on the transmission line, and the location is related to the length of the line. So the first thing we need to understand is the total length around the full circle correspond to a half wavelength on the line. And to find the impedance at a length from the low, basically you first find the location of your low and then rotate the low impedance point on the SWR circle by the length toward the generator, which is along the clockwise direction. And then you can read the R and X from the point on the SWR circle. And this will give you the input impedance at the particular location on the transmission line. And then we also derive two same expressions and argue that on the real axis, the RL value intercepting the SWR circle give you the standing wave ratio of the transmission line. And we also talk about how to locate the signal maxima and minima on the line, and we concluded that the signal maxima and minima correspond to locations on the real axis. So if you just move on the SWR circle, and whenever you intercept the real axis, then you'll be measuring the maxima or minima values of the signal. So this is a few key points I want to make for this session. Thank you.